In this part, we are going to use a small signal analysis approach to analyze the BJT-based amplifier. For BJT as a signal amplifier, if we configure it as the common emitter amplifier circuits, so the total base to emitter voltage and VBE here will be the DC voltage and plus our AC voltage here. So correspondingly, so the total collector current can be described by this formula, and if we plug in the both DC and AC voltage, and then we are going to get and this formula here. Actually, for the first two parts is only related to the DC signal. For example, here is only VBE here, and RS is the saturation current. So this is some kind of a constant, which is the DC collector current. And if we write this term as our capital IC and plus this AC term, and we get our total current at the collector side. For a small varying signal VBE here, if this signal is small enough, for example, if it's much less than 2 VT here, VT is the thermal voltage, which is 25.4 millivolts. So total will be close to 50 millivolts. So if this VB is less than 50 millivolts, actually the above equation can be further simplified or can be approximated by this formula here. And then we can see the total current will equal a DC components and plus a AC components. And if you look at this AC components, is very interesting. So this factor here, IC and divided by VT is some kind of a constant that is related to the DC collector current, and then VB is the varying small signal at the base. Now we get the time varying current, which is the second part in the previous equation. Now we can define some term. For example, is GM here. We can replace this IC divided by VT by GM, and then we can define a GM, make it equal RC divided by VT. As you remember in my part 1, I mentioned that the GM actually is defined at the working point if we take the slope measurement on the current versus voltage characteristics. Now this is the collector current, and this is the base voltage. Now this is the definition. Actually, we can also get the GM where GM equals IC over VT directly from the definition. And noticing that this is the collector current, which will include both DC and AC signal. If we take the derivative of this current with respect to the base current, the base voltage, and we take the derivative, and then we will be able to get the derivative equals the current divided by VT. And we know this at the particular point, at a particular one point, if we plug in, make RC equals IC here, as we can see, because this GM is defined only at that point. If we replace this small RC by capital IC, and we get the same formula as we get from here. So apparently GM, the transconductance GM, can be calculated by the DC collector current divided by our thermal voltage. For example, for IC current equals 5 milliamps, usually we can get a GM equals 0.2 amps per volt here. But remember, here the unit of the GM is amps per volt, because this is the current and this is our voltage. In order to figure out the voltage gain, and we can apply a KVL analysis and along these branches from VCC to the ground by including both the DC and AC signal here. From this formula, we can see VC is the voltage at the collector, which is also equals VCE, and it's supposed to equal VCC minus the voltage drop, or cos the RC here. So the voltage drop cos RC equals IC times RC here, and we plug in this RC by its both the DC and AC components, and then we can get a DC voltage here, and then in addition to some kind of AC voltage. So this is the DC voltage and this is the AC voltage we get. So the voltage at the collector, the DC voltage at the collector, and which is the first part, and the AC voltage at the collector, which will be the second part, and we notice a negative sign here. We know VC is supposed to equal VCE, right? Because the emitter side is being grounded already. So VC equals negative RC, and if we plug in this value as we obtained before, if we go back to the slides, so the time varying current or equals GM times VBE. If we take that, now this is the time varying current with the AC current at the collector equals GM times VBE. If we plug into this formula here by replacing the time varying RC by GM VBE, and we are be able to get our VCE equals negative GM VBE RC and negative GM RC times VE here. Now from this formula we can easily get our gain, right? Because the gain is defined by the output divided by the input, and that equation will directly give us this formula. And again, remember in the first part we also define the small signal voltage gain is by looking at this VC versus VBE here by taking a slope at this working point. Actually, these two actually are the same thing. We also notice the result is negative, which means the gain is negative. A negative gain also means this is an inverting amplifier, and that means if you input a signal at a 0 degree, and I will give you a 180 degree shift on the signal. And the transconductance of GM is a very important parameter for the amplifier. So since the voltage gain is totally directly proportional to this GM, now the GM actually for the BJT usually is much larger for the MOSFET. Let's recall the small signal model for the diode we have learned before. And in the diode, we have this IV characteristics, and if we find a working point, and we can also find a slope here. So that slope is equals 1 over RD. This RD actually can be calculated by NVT divided by RD. The reason for that is because our diode current will equal some kind of a constant diode current and times some time varying diode current. We can use a similar approach now here to analyze the transistor, especially the EBJ, right, the emitter base junction. We can define a small signal input resistance for BJT. So there are two input resistance we must first to take a look. The first one is called RPA. Actually, I mentioned RPA at the very beginning in the first part of the introduction part. RPA is defined as the input resistance between the base and the emitter, which is which can be seen looking into the base. If we define a current into the base, that is RB here, and if we have voltage and VBE, and then this RP is being defined by and VBE divided by RB here. Now RE is it's called active mode input impedance between the base and the emitter by looking into the emitter side, for example, on the right-hand side figure. And if we have a current RE here, and then we have our voltage VBE, and this VBE divided by this current will give us RE. Apparently, this RE current is much larger than the RB base current, so which means the RE is going to be much smaller than this RP, which will give us this equation here, this formula here, RP equals beta plus 1 times RE. Assume the transistor in this circuit. Now this is a common emitter circuit, also the common emitter circuit. And if it is operated in the active mode, and we have this total current will equals DC current plus or AC current, which we derived before, and our base current will be the collector current divided by a beta number, right? This, if we plug in this RC here, and we have this formula. As we notice, the first portion will be the DC component. So the second portion will be the AC components. So these AC components and divided by beta will give us the small signal current into the base, right? That is a small RB here. Now, remember the definition of the RP. RP will equals VB divided by RB. We just plug in RB, we just derived, and eventually we will be able to get a formula to allow us to calculate this RP, which is beta divided by GM here. So beta is an active mode small signal input resistance of the transistor between the base and the emitter, which is seen into the base terminal. Now, for example, for beta equals 100, this is a typical value for BJT, and the RP will probably equal like 500 ohms when RC equals 5 milliamps. Now remember, this RC here will change this GM value. This transconductance equals VT divided by RC, right? This is a collector current dependent parameter. If we get a different current, we are going to have a different value. Apparently, we'll have a different input resistance. Now let's find out how to determine the RE value. Now, in order to determine the RE value, we need to figure out and how much is the RE current. The RE current first. Now, we know the total emitter current can be calculated by the total collector current divided by alpha, right? That's the equation we obtained before. And we also have two components. One is the DC components, another one will be the AC components. So this one will give us the AC components of our RE here. Now this is the formula we obtained before, and we plug in that, and we will be able to figure out how much is our RE, right? So if we plug in that, and we will be able to get this equation 3 here. And from this equation here, we can easily tell how much is our input impedance seen from the emitter side. Again, this is the definition of this RE. It equals VE divided by negative RE, because we are seeing into the emitter, so the direction actually is against our current flow. Our VE here need to equal negative VBE, because we are talking about in this loop, right? This VE has to equal a negative VBE. And if we replace our VE by the negative VBE, we get our RE here will equal VBE divided by IE. RE we already derived from our equation 3. We just plug in, and then we eventually will be able to get this formula here. From this formula, and we can easily calculate our RE here, or input impedance RE will equals alpha divided by GM. We know alpha is a value which is very close to 1, so this is approximately equal 1 over GM. For beta equals 100, RE equals 5 ohms at IC equals 5 milliamps. Compare to the previous repair, we can see this value actually is much smaller. And here I can show you how we can get the relationship we showed you in the previous slides. Repair will equals beta plus 1 times RE. Now from the definition of transconductance, now this is the definition, and this will give us the calculation formula. And also the input resistance for repair is defined by VB divided by RAB. And this is the formula to allow us to calculate our repair here. The input resistance at the emitter is defined at VB divided by RE, and this is the formula which allows us to calculate. And based on those formulas, actually, we can easily to get this final formula here. Now we know RC and RE, they are buying a factor of alpha here. Alpha is a value close to 1 but less than 1. Now our pay will equal beta VT divided by alpha RE, right? Because I replace the RC by RE times this alpha. Now VT divided by RE actually is our RE, right? From this formula here. Now we can tell our pay will equal beta divided by alpha. And here is the relationship between alpha and beta. If we plug in, we can easily get our pay equals beta plus 1 times RE. And is obvious. Now this R pay is different from RE, right? Now with this R pay and this RE value, actually, we can develop the small signal analysis model for the BJT. Now the first one is called a hybrid pay model. The hybrid pay model is a very popular model for small signal analysis of BJT. Now there's two versions of this model. One version is the voltage controlled current source, and we have a voltage input to the base, that is VBE. This one will control a current. That current is GM-VBE. We analyzed it before. So this is a voltage controlled current source. And we can also see this is a current controlled and current source. Now we have a current into the base, and through this resistor I here we just derived, and then we are going to control and this current equals beta times RB, right? This relationship, this beta RB equals RC has been derived in the first part. If we consider the early effect, so the early effect, remember, will give us some kind of output impedance. Now this output impedance will be in parallel with our amplifier. So we just put in this in parallel with our amplifier, and this will give us the modified hybrid pay model with considering the output impedance. And again, there's two versions, right? One is the voltage controlled current source, another one is current controlled current source. With the including of this RR here, and this will make the original small signal voltage gain will change a little, right? Original small voltage gain equals negative GM times RC, because now this RC is being in parallel with a small RO here, and then we're going to have a RC in parallel with this small RO. Looks like the introduction of this early effect will reduce our small voltage gain here. There's another model which is convenient to do the analysis. That is called small signal T model. So the T model is an alternative model but it is useful at certain conditions. For example, for the emitter follower, we are going to analyze in the future. And in this T model, we also have two versions here, right? One is also the voltage controlled current source. Now this is our VBE, which is, but now the VBE is applied to this RE here. We just derived the RE value. And it will control the current at the collector side, which can be calculated by GM times VBE. And the second version of this model is a current controlled current source. Now this current is our RE here. Because RE is related to this RB, right? You can also call this RB controlled RC here. It's current controlled current source. Again, if we consider the early effect and we needed to include the output resistance from the transistor, that is RO here. Now this RO will be in parallel with this transistor again. So far, all our analyses are based on NPN transistors. But for small signal analysis, actually, they will be exactly the same. There's no difference. So the difference for PNP and NPN transistor is for their DC bias, is not for small signal analysis. So for DC bias, you may need to consider the polarization and for the EBJ and the CBJ direction. But for small signal analysis, as we can see, and we will model those junction using a resistance value, so we don't care the direction. So that's why no matter PNP or NPN transistors, their small signal analysis will be exactly the same. Okay, I think that's conclude this part.